Let's specify the material properties and boundary conditions. So I'll come back to say body select here and just highlight geometry in the tree. I need to go back to the main workbench window. Right now, if I expand materials, the only material available is structural steel. And if I go to say the core, it's automatically assigned. So let's change that. So I'll go to switch windows option, go back to the main page, select right click on engineering data and say edit. And that will bring up this tab over here, and I will say add new material. So I'll call it face sheet material. You can give it the actual name when you're if you want to when you're doing this in real life, and I'll say linear elastic isotropic elasticity. So that's the simplest form of 3D elasticity. So I just dragged isotropic elasticity to face sheet material, and I'll expand isotropic elasticity and enter the Young's modulus, which is 6.3 e to the power of 10 to the power of 10 in this demo, and the Poisson's ratio is 0.3, and that should be, that's similar to what I showed you before, or the same as what I showed you before. And I'll say enter. So I have my face sheet material. Similarly, create the core material. So I have created the core material by clicking, add new material. I've dragged isotropic elasticity onto that, and then I've entered the value of the Young's modulus, which is 2.7 e to the power of 7 pascals, and Poisson's ratio is 0.0547. And ANSYS automatically calculates the shear modulus using this formula. So we've given it E and nu, and it calculates G, and that's 1.28 e to the power of 7, which is what we are really interested in. And you can, change this as you change your design. You're not required to do it in this particular exercise. Okay, so now I've added my face sheet material and core material. I'll come back to the project tab, and to bring it from engineering data to model, I have to right click on model and say refresh. And this, and get a tick mark. This symbol is a refresh symbol. And now if I go back to mechanical, I see I have the face sheet material. I can check, highlight it and check it has the right value of Young's modulus and Poisson's ratio, and similarly for the core material. So for the core, I will assign it to be core material, and I can control click on bottom and top face sheet and assign both to face sheet material. I can do them one by one, or I can control click and do it for both. So at this point, the governing equations are defined. Young's modulus and Poisson's ratio are, you can think of them as constants appearing in the governing equations. The only thing left to do are the boundary conditions. Let's do that. I'll highlight static structural in the tree. Now, this is a cantilever type of setup. So where the wing spar is attached to the fuselage, we will set all three displacements to 0. So let me just pin these and hit Z to zoom out, or I can click zoom to fit, translate, and then rotate using the middle mouse button. So you have to kind of manipulate the model to see the other end and zoom in. It's a little awkward working with a long slender beam. let me zoom in a little bit here. Okay, so I'm looking at the fixed end, and I'm going to set all three displacements to 0 at that end. So I'll click on displacement. I have to highlight static structural in the tree, and I'm going to set it to surfaces or faces. So I'll click on this surface. I need to zoom in probably a little bit more, and then control click on these two. So I select all three surfaces, the two face sheet surfaces and one core surface, and say apply, and I'll see three faces, and I will set all three components of the displacement to 0. And so that's my displacement boundary condition. And then for the force, let me go back to the isometric view. And what I'll do is I want to apply a force on the top surface. So I'll click on the top surface, say apply here, and define by components. And the y component, so this is, let me go back to the PowerPoint slide. The wing loading per length is 32.7 and the wing length is 15. So I just need to multiply 32.7 by 15, and I'll get the total force on that surface. And answers will distribute that uniformly. So I will say equal to 32.7 times 15, and that comes out to be 490.5. So at this point, the governing equations and boundary conditions are defined. Let's resave the model. So I'll go here, and I'll say File, Save. And at this point, you may want to also do File, Archive, and overwrite the WBPZ archive, and then go back to the temporary files folder and copy this to your OneDrive. And then I'll come back to ANSYS, and then I will actually in the next video I will hit solve and then look at the results.